What's up, everyone? Welcome back to Speed, Math, and CS. So today we are going to be continuing our study of AP Calculus AB. Yeah, I know it's been a week since we last covered it, but we are back once again with Unit 2, which is going to be talking about derivatives, right? So essentially what we learned last lesson, right, is we learned about limits, right? And limits can be used to approximate things to infinitesimally small values or infinitesimally large values, right? So for a derivative, right, the limit used to define the slope of a tangent line is also used to define like differentiation, right? So the derivative is defined by something like so, right? F prime of x, right? This is how we're going to denote the derivative. It's using this like sort of quotation mark, but we call it f prime of x. Will be equal to the limit as delta x approaches to 0 of f of x plus delta x minus f of x over delta x. So as you can notice here, right, this looks a lot like a difference quotient, right? And of course we can't just plug delta x in because it will result in 0 over 0. But essentially, yeah, so this notation on the left, you read this as f prime of x, but this difference quotient is essentially going to be our derivative function, right? So the derivative of a function of x is also a new function of x, right? And this sort of new function will give the slope of the tangent line to the graph of f at the point x comma f of x, provided that the graph has a tangent line at this point. The derivative can also be used to determine the instantaneous rate of change, or simply the rate of change, of one variable with respect to another. The process of finding the derivative of a function is called differentiation, and a function is differentiable at x when its derivative exists as x and is differential on an open interval a, b, when it is differentiable at any point in the interval, right? So in addition to this f prime of x, there are several types of notations that we can use, right? So the most common other ones we'll see in calculus are dy of dx. This essentially means you're taking the derivative of y with respect to the variable on the bottom, which is x. And then this notation is going to be more like helpful once we get to actually solving differential equations, which is going to be unit 6, right? So unit 6, we are going to be, these two are called differentials, essentially. The top, like dy is a differential and dx is a differential. So in unit 6, we are going to be learning how to split these two differentials, take integrals, things like that, in order to solve a variety of different equations. But essentially, we're going to first start by finding the derivative using the thing called a limit process, right? So let's try to first find the derivative of using this. We'll just do one practice on the limit process, and then we'll get into the actual rules regarding derivatives, right? So practice problem number 1, right? So how would we take the derivative of f of x equals to 3x? X to the 3 plus 2x. How do we take the derivative of this, right? So essentially what we would have to do is we would have to essentially use the limit process, right? So we know that f prime of x will be equal to f of x plus delta x, right? So it'll be equal to x plus delta x to the 3 plus 2x plus delta x minus x cubed minus 2x, because we had to subtract f of x, all over delta x, right? And now at this point we can use like pre-calc and algebra 2 knowledge to simplify this, right? So then f prime of x will be equal to x to the third plus 3x squared delta x squared delta x plus 3x delta x squared plus delta x cubed. And for reference, these delta x's are all in parentheses, right? And then plus 2x plus 2 delta x minus x to the 3 minus 2x. So you can see, right, and then all of this over delta x. So you can see right away, we can cancel out a couple of terms, right? So these 2x will cancel out with the negative versions. And now you see we can simplify all of this, because at this point, now actually, this is very important and I forgot it, but this is limit as delta x approaches to 0, right? Same thing here, limit as delta x approaches to 0, right? So as you can see here, now that we've canceled out all the terms with just x, there's a delta x in every single one of these terms, meaning that we can divide this out. So now, if we do divide it out, right, then we are going to get 3x squared, or actually, sorry, I keep forgetting this, but we are going to get the limit as delta x approaches to 0 of 3x squared plus 3x delta x plus delta x squared. And then lastly, plus 2, right? Something like so. So now what you'll notice is that in order to solve for the derivative, we can just use limit substitution, right? So we can just plug in 0 for all the delta x's, right? So these terms will cancel out and these terms will cancel out, meaning that after this, we are left with 3x squared plus 2. And this will be our derivative, right? So using the limit process, we have successfully found a derivative for the function, right? And then if we wanted to, let's say we wanted to, the problem was instead asking us to find the derivative at, or the problem can give you a point, right? The problem can either say, hey, find the derivative at 1, 2, or find the derivative at x equals 1, right? It can be either of these in the AP test, right? When it asks you to solve via limit process, right? But all you have to do in this case is you just take your derivative, right? You can just plug in 1 for x, right? And then if you plug in 1 for x, you will get that this equals to 5, right? So essentially, if you were to write this in notation, right, this would mean that f prime of 1 equals to 5. And now if you were given, regardless of what you were given here, if you were just given the x value, all you have to do is just plug it into this equation, right? So plugging it into equation, this is actually going to be 3, not 1, 2. So it's going to be 1, 3. But if you plugged in x equals 1 into the equation, you'd get 1 plus 2, which is 3, right? But the best case is if you're just given the point, right? And then now another type of question could be they ask you to solve for the actual equation of the tangent line, where we will use point slope form, right? So remember, point slope form for a tangent line looks something like this, right? And plugging in f prime of x will give us our m, right? So all we have to do is y minus 3, because our point is 1, 3, times 5x minus 1. And it should be pretty obvious how to simplify this, but yeah, just make sure on the actual AP test you simplify this just to make sure. but this is what our tangent line is going to look like. So you could receive either one of those three problems, and this is just a type of problem you could receive on the actual thing, right? So now, before we actually get into talking about the rules regarding derivatives, we have to talk about differentiability and continuity, right? So let's actually draw. If we have another, let's draw another limit form of a derivative, right? So f prime of c will be equal to the limit as x approaches to c of f of x minus f of c over x minus c. Something like so. And you'll recognize this as an alternate form of the derivative because this is just using our slope. This is just using our slope formula, and we are just bringing the points infinitely close to each other because as x approaches to c, remember a limit is bringing something infinitesimally close to c but not equal to c, right? So they will essentially get the instantaneous slope or the derivative by doing something like so. So essentially what this means, right? So this will give us a slope of a secant line, right? So if we just don't take this limit into account, right? This will essentially give us a secant line, which looks something like this. So let's say we were taking the derivative and let's say c was here, right? Now we can try different points, like we'll call this x1, right? Then we're gonna have a secant line drawn between these 2 points, something like this. And then our limit essentially says we will bring this closer and closer. So as we bring it closer and closer, the secant line will start to approach the tangent line at the instantaneous slope at c, right? So remember that the existence of this limit, right? For this, we would have to split this into 2 one-sided limits, right? But essentially, the one-sided limits would be called like derivatives from the right and derivatives from the left, right? And essentially what follows is that f is differentiable on the closed interval a and b, where when it is differentiable on a, b, like open interval, when the derivative from the right at a and the derivative from the left at b both exist, right? So let's talk about our rules for continuity in derivatives. I keep saying differentials. In derivatives, right? So essentially a derivative is continuous for under 2 cases. First, or under a couple of cases. First, it has to be continuous. It has to be the actual function has to be continuous at the point we're taking the derivative. And second, we can't have a sharp turn. And also, the function like can't be a vertical line, but it will essentially slope can't be vertical at that point. Because if it was vertical, we would say, okay, slope could be infinity, but we will, for the purpose of this, we'll say that the slope doesn't exist, the derivative doesn't exist at that point, right? So essentially, the function itself has to be continuous. So this will break up into its own three rules, like we discussed last time for continuity, right? But yeah, so these will break up into its own 3 rules, where f of x has to exist. F of x has to exist. Limit as. Sorry. This is actually supposed to be represented with the c. Sorry. C exists. Limit as x approaches c. c exists, and lastly, f of c equals to limit as x approaches to c of f of x. Right? So continuous breaks up into its own three rules. But essentially what it means by no sharp turn is essentially if we take a graph of something like so, right? Let's say we have something that looks like this, and then we have a sharp turn like that. At this point right here, right? That point at the top, right? It's not differentiable because at that very point, we don't know if we want to consider the negative slope or the positive slope or anything in between, right? So if there's a sharp turn like that, the derivative doesn't exist. And of course, if it's vertical, right, it doesn't exist. So yeah. So what we can conclude, right, is that on the AP test, if they tell you a function is differentiable at x equals to c, then it must be continuous at x equals to c. So differentiability equals to continuity, right? Because remember, if they tell you that it is differentiable at that point, that means it's continuous at that point, there's no sharp turn, and the slope can't be vertical. And not being continuous at the point, and being continuous at the point mean all of these three are true, right? So essentially that's the main concept. So now let's get into our basic differentiation rules and rates of change. So we're going to start by the derivative of the function using the constant rule. Then we're going to learn about power rule, then constant multiple rule, sum and difference rules, and then we're going to look at the derivative of the sine function and the cosine function, and lastly, we're going to do rates of change, right? So let's start by the constant rule is more of an obvious one, right? But essentially, what the constant rule says is that if f of x equals to some constant c, then f prime of x equals to 0, right? So essentially, if you think about it, right, f of x being c, that's a horizontal line. So yeah, so the derivative of, if you think about a derivative is slope, right? So if f of x equals c, that's a horizontal line, the slope is going to be 0 at all points. So f prime of x equals 0, right? That's gonna be, I don't know why I put a 2, but this is going to be the first rule, right? And then our second rule is going to be power rule, right? So essentially, the power rule is going to state that if f of x equals to some x to the n, right? Some x to the n, f prime of x is going to equal to n times x to the n minus 1, right? So essentially we take this n, bring it out in front, and then subtract 1 on the power. So this one is a little more complex, right? But essentially think about this, right? If we have a function like so, taking the derivative, we bring this out in front and reduce the power, right? So 3 comes out in front, and then now we have x squared. If we take the derivative of this, we now have 6x, because this will be x to the 1, right? And then now, if we use power rule again, right? Just don't, like, derivative of 6x, right? It's 6x to the 1. We bring a 1 in front. It doesn't change this constant. But now we have an x to the 0. So taking the derivative again will be 6. And then if we take the derivative again of 6, we are going to be at 0, right? So you can see how, like, taking the derivative over and over again, you can see how we actually apply this power rule, right? So, yeah. So essentially, let's actually do like a couple of practice problems on power rule before we move on to our next rule. So I'll actually do this to the right, just so we don't, like, I want to keep all our rules in one space. So let's actually do this to the right. But let's start off with the practice problem, right? This will be practice problem number 2 for today, right? But let's try to find we've already found the derivative of x cubed. So let's try to find if f of x equals to cube root of x, let's try to find what f prime of x is. So in this case, right, we have to first do a little conversions in order to use power rule, right? So we have to convert this f of x into the form x to the 1/3, something like so, right? And then in order to evaluate f prime of x, we have to essentially bring this 1/3 out in front, right? So if we're evaluating f prime of x, right, we bring the 1/3 out in front, and if we reduce this power by 1, we get we get x to the negative 2/3. Typically on the AP test, you are allowed to leave this something like this, but let's actually simplify this further because let's just practice using our algebra 2 and pre-calc knowledge, right? So f prime of x will be equal to, because it's a negative, right, we will put this in the denominator, 1/3 cube root of x squared, right? So it'll look something like this, right? This will be like a simplified final answer for our derivative, right? Now, let's do another practice problem, right? So this will be practice problem number 3 of the day. So let's try to find the derivative. Let's say y equals to 1/x squared. What is dy over dx? Right? So now what we are going to do is we are going to first convert this into something where we can use the power rule. So remember, in order to use the power rule, it has to be in the form x to the power of something. Then we can use power rule, right? Otherwise we can't. But in this case, we can just convert it, right? We can convert this to y equals to x to the negative 2 using our negative exponent rule. And then if we apply power rule here, we will get that dy over dx is equal to, let's start by bringing this constant out in front, so negative 2 x, and then we have to subtract 1 from this power, so it'll look something like so, right? And then if we simplify this even further, we will get that it's equal to negative 2 over x to the 3, right? So something like so will be our final answer. So hopefully we should be very comfortable with how something like this works, right? So, and then remember, if we are given the equation, let's actually do a practice problem with this. So this will be practice problem number 4 of the day, right? Practice problem number 4. So let's say we have to find the derivative of, let's say we have a function like so, and we are asked to find the tangent line we're asked to find the tangent line going into 1, 1, right? We're asked to find the tangent line at 1, 1, right? So the first thing we have to do in order to find a tangent line is we have to find slope. And to find slope, we have to take the derivative, right? Let's convert this into something usable by power rule, right? And then to calculate dy over dx, which will be our slope, dy over dx, or actually, it'll be better if we note this as y prime, right? As y prime. So y prime will be equal to -3, bring the -3 out in front, reduce the power. It'll look something like so. We go from here to here, right? So now if we want to calculate the slope at the point 1, right, we simply plug in 1 for this. 1 to the power of anything is just 1. So we get that this is -3. So now let's use point slope form, right? So point slope form, y minus 1 will be equal to -3 times x minus 1, right? Because we just plugged in 1 comma 1 here, and then we plugged in the slope of -3. So then now if we distribute, I keep saying differentiate. If we distribute, we're gonna get this as our tangent line to this graph of 1 over x and 3 at point 1 comma 1. So hopefully this should be good practice with all the stuff we've covered up until now. So now let's move on to our next rule, right? So the next rule is the constant multiple rule, right? Which essentially says that if f of x equals to c multiplied by some g of x, right, then f prime of x equals to c times g prime of x. And all this means, right, is essentially that a constant multiple won't matter. So essentially, let's do a practice problem on this. So practice problem number 5, right? So let's say we have to find the derivative of 4 over x to the 2, right? Let's say we have to find the derivative of, so what would y prime be equal to, right? First, let's convert this into a usable form of the power rule, right? X to the -2. And essentially what our constant multiple rule says is that we can treat this as if it's not even part of the thing, and then we just multiply by 4 at the end. So we would just take -2 out of the top like we always do, right? So y prime would be equal to -8, but now we multiply by this constant multiple out in front, and then we reduce the power by 1. So our final answer will look something like this. So for constant multiples, the derivative of a constant multiple is like, we don't worry about that. So if we had to find the derivative of 4 times g of x, right, that derivative would just be 4 times g prime of x. So essentially the constant multiple at the front, we don't have to worry about that. We just multiply it out at the end. So so something like so, right? Now let's go on to the sum and difference rules, right? So these will be, rule number 4, right, for derivatives will be that why did I write this in red? If f of x equals to g of x plus h of x, right, it's going to, then f prime of x is going to be equal to g prime of x plus h prime of x. And then this is essentially the same as, so we can actually make a corollary for this rule, right? So if f of x equals to g of x minus h of x, right, it's the same thing. H prime of x is going to be equal to g prime of x minus h prime of x, right? So now let's do a practice problem on this where we will use a constant multiple rule, and we are going to use what we've just learned, sum and difference rules. So this will be problem number 6 for today. So let's say we're trying to find the derivative of 4x cubed plus 8x squared, right? Let's say we're trying to find the derivative of this, right? So, or actually, just to make this simpler, let's say y equals to this, and we're trying to find what y prime is equal to, right? So, first thing, right, we can actually just directly apply power rule, right? So, y prime is going to be equal to, bring this 3 out in front, it's going to be a 12, right? When we bring this 3 out, we just multiply by whatever constant multiple is in the front, and we reduce the power, right? And now, because of sum rule, we can just add the derivative of this side, right? So if we want to find the derivative of this whole thing, the derivative of this whole thing is just the derivative of this. So let's actually draw this. If we wanted to find the derivative of that whole thing is just equal to the derivative of this plus the derivative of that. That is essentially what the sum and difference rules tell you. If we have a plus or a minus in here, we can just take the two derivatives of the original things and then just plug them in, right? So now if we take the derivative of 8x squared, we bring the 2 out in front, it's going to be a 16, right? Reduce the power of x squared by 1, so it's going to be x now, right? So we have found the derivative. So that is going to, let's actually do a second one, just to make, and we'll do this one with difference rules. So we problem number 7, right? So let's say that y is equal to 6 over 6 over x squared minus 8x to the 4th, right? And then we want to, what would y prime be equal to, right? So we can't just directly apply power rule here. We have to first solve for this function in terms of a constant multiple times power. So x to the negative 2 minus 8x to the 4. Something like so. This is what it's going to look like, right? So now if we wanted to find y prime, right? Remember, bring this negative 2 out in front. It's going to become a negative 12. X, we reduce this power by 1, so it's going to become x to the negative 3. And then we are going to subtract, right? We can just subtract this because the subtraction rule says that to find the derivative of this whole thing, all we have to do is find the derivative of this part and the derivative of this part, and then find the difference between the two. So let's now, if we take the derivative of this, take the 4 out in front, so it'll be 32. 32 multiplied by x, reduce this power by 1, so it'll be x to the 3. So, that's over to 32. But this will be our final answer. So hopefully this should give you a good understanding of power rule, constant multiple rule, and our sum and difference rules, right? So let's talk about the derivatives of sine and cosine, right? So essentially the derivatives of sine and cosine are something like so, right? We'll learn the derivatives of other trigonometric functions later, but all you have to know for now are the derivatives of sine and cosine, right? So our first rule is that if f of x equals to sine of x, right? F prime of x, right? If we take the derivative of sine, we get cosine of x, right? And then if we do a corollary of this, right? F of x equals to cosine of x, right? Then f prime of x equals to negative sine of x, right? This is a pretty simple rule, right? Derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. So let's do a practice problem. Right? This should be pretty easy to understand. But let's like mix and match everything that we've learned so far with like a quick practice problem with the sine and cosine, right? So problem number 8, right? Let's say that y is equal to 3x to the 4th plus 8 sine x multiplied by 2 or minus 2 cosine of x. Or actually, let's just make this problem interesting. Let's actually say this is 8 of sine x multiplied by. Oh no, actually we can't solve that yet. We haven't learned chain rule yet, so we can't solve that. So let's do something like so, right? So y equals to 3x to the 4th plus 8 sine x minus cosine of x, right? And essentially with this, right, what we have to do is we're going to be asked to solve for y prime. What is y prime if y looks something like so, right? So we can directly take the derivative, right? So put this 4 out in front, so it'll be 12x to the 3, right? The derivative of sine is cosine, so this just become 8 cosine of x, right? And then derivative of cosine is just negative sine. So it's going to become plus sine of x. So this is our final answer. All right. So this should be like, if you want to try this out in your graphing calculator, it'll look exactly the same. But this is essentially how we are going to be working on it, right? So now let's talk about rates of change, right? Rates of change real quick before we move on to our next derivative rule, right? Because we're learning all derivatives today, right? So by the end of today's lesson, you should be extremely comfortable with like any derivative I toss at you, any function, you should pretty much be able to take its derivative. Like we won't be talking about like logarithmic functions or exponentials, but other than that, we are going to be talking about everything you need to solve derivatives. So let's talk about rates of change, right? So we've already seen how a derivative is used to determine slope. So the derivative can also be used to determine the rate of change of one variable with respect to another. Applications involving rates of change, sometimes referred to as instantaneous rates of change, occur in a variety of fields. And a few examples of these are population growth rates, right? So taking the slope of a population, production rates, so taking the slope of production, water flow rates, taking the slope of water flow, velocity, which is taking the derivative of position, and acceleration, which is taking the derivative of velocity. So a common use for rate of change is to describe the motion of an object moving in a straight line. So in such problems, we usually use a horizontal or vertical line with designated origin to represent the line of motion. On lines, movement to the right or upward is considered to be in the positive direction, and movement to the left or downward is considered to be in the negative direction. So the function s that gives the position of an object of time t is called a position function. And if over a period of time delta t, the object changes its position like so. So let's actually draw this out, because we'll draw this out over here, right? But essentially, if we take a position function, right, delta position is represented with an s, right? So delta position is going to be equal to something like so, right? Because remember, s of t gives us the position at time t. So if we want to find the change in position, we have to take the new position, which is going to be s of t plus delta t, right? The time that changed, minus the old position. So new minus old is our function for deltas. So the old is just minus s of t. So essentially, right, you know the familiar formula, right? That rate equals to distance divided by time, right? So we can define average velocity, right? We can define v average to be equal to delta s divided by delta t, right? So if we try to find let's try to find the velocity using position, right? So problem number 9, right? So let's say Steve throws a ball, right? I don't know. I'm thinking of Steve because we just saw like the Minecraft movie and things. So I'm thinking of Steve. But whatever. So let's say that Steve throws a ball up, right? And this is the position of the ball, right? As a function of time, right? So negative 16t squared will be gravity, and we start it at a height of 100 meters, like so. So the question is, what would our function for velocity be, right? What would our function for velocity be? So in order to do this, right, since velocity is just the derivative of position, it's literally as simple as taking the derivative of this, right? So we simply will apply power rule, take this 2 out in front, negative 32t. And then remember, this plus 100 doesn't matter because the derivative of a constant is just 0. So this is going to be our velocity function, right? Something like so. And in fact, let's extend this with a 10th problem, right? And let's try to find the acceleration, right? So the acceleration is equal to derivative of velocity, right? So just writing this in like plain words, right? So velocity equals to the derivative of position, right? Acceleration equals to the derivative of velocity, or we'll actually cover this later, right? But essentially the second derivative of position, right? And a second derivative, right, essentially means that we take the derivative twice. So we take the derivative of position and we get velocity, and then we take the derivative again to get the double derivative, or the second derivative, right? So this is what these double quotes mean. And usually we'll only say single quotes and double quotes, but there can also be like triple quotes, which means we take the derivative 3 times and things like that, right? So let's say we now have this extension of this problem where we're trying to find the acceleration. So given this velocity, right, if we could just apply power rule. So v prime will be equal to t to the power of 1. If we take the 1 out of front, it's still negative 32. Reduce the power of t by 1, right? We're going to have t to the 0, which is just 1. So v prime will be equal to this, equal to just negative 32. And this is essentially going to be how we apply this, right? But now for an 11th problem, right? For problem number 11, let's try to find v average. V average of this if s equals to negative 16 t squared plus 100, right? Of 100, right? Over the interval, say 1, 2, right? From 1 second to 2 seconds, what is the average velocity? In order to do so, we will just use our slope, or we're just going to use our slope, our average slope function, right? So we know that average slope equals to, like, we know that average slope, right? So in this case, we're trying to find v average, because v is the slope of instantaneous slope of s, v average is the average slope. And from pre-calc, we already know average slope to be equal to, or I have my eraser, sorry. there'll be s of 2 minus s of 1 over 2 minus 1, right? And if we plug in 2 and for this, right, we'll get negative 64 plus 100, which is going to be 36, right? And then if we plug a 1 in there, it's going to be 84, right? So it's going to be 36 minus 84 over 1, right? So the average velocity is just going to be, across this interval, is just going to be negative 48. Yeah, negative 48. So this is how we calculate the average velocity. And we do so using something like that. And using the derivative to find velocity is exactly how we did it here, right? So the position is given here. So the velocity is the derivative of position, and acceleration is the double derivative of position, or the derivative of velocity, right? So that is how we actually do this. So now let's move on to doing more. We took a quick tangent here with the rates of change, but now let's get back to putting more. Let's get back to putting more rules under our set of derivative rules that we've derived, right? So now let's cover product and quotient rules, right? And then afterwards, we're going to also take some higher order derivatives. So, and then we're also going to discover the derivatives of other trigonometric functions, right? So our first rule is the product rule. So essentially, the product rule states that if f of x equals to g of x multiplied by h of x, right? F prime of x equals to g prime of x times h of x plus g of x plus g of x multiplied by h prime of x. Something like so, right? So this is actually not what you would expect. So let's do a quick practice problem. So this will be practice problem number 12 for today, right? Practice problem number 12. So let's try to find the derivative of, if y is equal to 3x squared cosine x, right? What is y prime? So the first thing to do is split this, right? Split y into 3x squared multiplied by cosine of x. And then now if we use product rule, we get that this is equal to, if we take the derivative of this first function, right? Derivative of this, bring the 2 out in front, it's 6, reduce the power, it's going to be 6x. 6x multiplied by just original cosine of x. Cosine of x minus 3x squared sine of x. So essentially what you do is we just add derivative of the first one times normal second one times normal first one times derivative of second, or plus the, sorry. We do derivative of first one multiplied by normal second one plus derivative of plus normal first one plus derivative of second one, right? So that will give us this function. Yeah, right? So product rule is probably our most confusing rule yet. But of course there'll be a lot of practice on the actual practice or homework that will be pushed out. So that is essentially how we will use the product rule. Next, let's talk about the quotient rule, right? So the quotient rule this time is not going to be a corollary of the product rule. So the quotient rule essentially says that if f of x is equal to g of x divided by h of x, right? that this says that f prime of x equals to g prime of x, or g prime of x times h of x minus, make sure this is a minus g of x times h prime of x, right? So, and then, h prime of x all over h to the x squared. This one's more complicated, so let's actually, you're going to have to, memorize this. There's no other way to solve this, but later when we learn about chain rule, in case, you keep forgetting this rule, we'll learn about how we can actually just, use product rule instead of quotient rule. So, it's actually not required that we ever use quotient rule, but it's helpful to learn because it will simplify stuff, and we don't want to have to apply huge chain rules. And we'll learn about chain rule later. Sorry if I'm not making sense, but essentially, yeah. Let's do problem number 13. Let's try to find the derivative of. So let's say y equals to cosine of x divided by 3x squared, right? So what would y prime equal to, right? So remember, the first thing that we can do is we could just take the 1/3 out in front, because the 1/3 is just a constant, so it won't matter. We take the 1/3 out in front, and essentially what we do now is we will have to use our function solving, right? So our quotient rule. So we take the derivative of. So the derivative of cosine is negative sine. So it's equal to negative sine of x, so 3 negative sine of x multiplied by x squared, right? Minus, minus cosine, minus 6 cosine of x multiplied by x all over this I'm using 3, right? Sorry. So yeah. So I don't know why I put this here. Yeah. Equals to 9x over 4. So just know that we can't simplify this any further, right? And yeah, you can see why quotient rule can be very messy, right? So hopefully you won't see a lot of this on the AP test, because this could get messy very quickly. So that is going to be our quotient rule. So rule number 7, right? So now we covered the derivatives of sine and cosine, but we never covered the derivatives of any of the other trigonometric functions. So let's talk about the derivatives of the other trigonometric functions. So the derivative of, in fact, I'm going to stop saying f. We could just write this as tangent of x, right? Let's say derivative of tangent of x equals to secant squared of x, or 1 over cosine squared of x, right? And the derivative of cotangent of x equals to negative CSC squared x, or in other words, it's equal to negative 1 over sine squared of x, right? And then you should already know what all these secant, cotangent, and CSC or cosecant functions are from pre-calc, right? So the derivative of secant of x equals to secant of x multiplied by tangent of x, and the derivative of cosecant of x equals to negative cosecant of x multiplied by cotangent of x. And don't worry, don't worry about like going back through the video and like writing down every one of these rules. At the end, I'll just like scroll through the rules just to make sure like you have time to write them down and actually like go practice them on the homework and things, right? So, well, actually, okay, so we actually don't have to, let's actually not do like a practice problem on this, because these are more of you just need to memorize it. It's not like doing practice will like actually like do anything, right? But so yeah, so now let's talk about like higher order derivatives, right? So we'll step away from our derivative rules again for a second, right? So I know, yeah, the most fun part of derivatives is learning more and more derivative rules, right? And seeing what random function can we take the derivative of next, right? So it's already been crazy. We've been able to find the slope of so many different things, right? But now let's talk about higher order derivatives. So essentially, I've already teased this earlier when we talked about the second derivative, right? But essentially, if we have f prime of x, or if we have f prime of x, we know that this is the derivative of f of x, right? So we know that this is equal to the derivative of f of x. F double prime of x, right? Remember, the double prime is equal to f prime of x, right? F prime of x, and now take the derivative of the derivative. And then the same thing going forward, right? If we have a triple prime, we take the derivative of the double prime, and the second derivative takes the derivative of the first derivative, and then the first derivative takes the derivative of the actual function. So at this point, we've taken the derivative 3 times. So what is this going to look like, right? Let's take an example of this will be what? Practice problem number, I'm trying to remember this is. I think this is 15, right? Practice problem number 15, right? So let's say so this won't really be a sort of a practice problem. It's going to be more of just like experimenting with this, right? So just so you understand how these work a little better, right? So f of x equals to x to the 4th, right? F prime of x is going to be equal to 4x to the 3rd, right? F double prime of x is going to be, we take the derivative of the derivative, so then we are going to bring the 3 out in front, 12x squared, right? And then triple prime of this, we bring the 2 out in front, so it's going to be 24x. And then when we want to denote anything with the 4th derivative or higher, we use something like this. We just say f2 like the in brackets 4, right? And this is essentially means that we take the 4th derivative, right? So then this is going to be equal to 24. And then lastly, if we want to take the 5th derivative of x, this is going to be equal to 0. So you can see how all the higher order derivatives work, right? So if we want to take the first derivative, we take the derivative of the normal function. If we want to find the second derivative, we take the derivative of the first derivative. If we want to find the third derivative, we take the derivative of the second derivative, and then so on and so forth, right? So this is essentially like a chain going down of taking the derivative of the derivative over and over. So this is essentially what a higher order derivative is, right? And it's going to be important for things like position and acceleration, right? So position is the double, and so acceleration is the double derivative of position because it's the derivative of velocity, which is the derivative of position. So you can see how that sort of works. So let's get into using chain rule. And I think this is going to be the chain rule. I think is going to be So we have to do chain rule and then implicit differentiation and then related rates. So chain rule is going to be the thing like that we're going to do. It's going to be the main thing, and it's going to require like a heck ton of practice, right? So this is going to actually be like a new rule here, right? And you can see there's going to be many cool and absurd ways that we are going to apply chain rule. Like chain rule is essentially going to completely rethink how we have been calculating derivatives, as it makes so many derivatives so much easier to calculate, right? So, and I'll actually show you some examples of how it actually makes like calculus in general so much easier. When we get to integrals, the chain essentially like chain rule or U sub is going to be used to make integrals like so much like easier to simplify, right? So let's get into chain rule, right? So essentially what chain rule states, right, is that so essentially what we can do here, right, is in this case we are going to use the differential notation again, right? So essentially what we can just think about this as a fraction, right? So if we want to say this is dy over du, right? So we want to take the derivative with respect to some u and then multiply. So we'll start with chain rule by taking something with respect to u, right? But essentially, what we're going to learn later, how we're going to start by just u subbing things, by substituting x's with values of u, right? But then later, we are actually just going to solve it directly and not worry about substituting for u's, right? So if we think about this as a fraction, if we multiply this by du over dx, right? If you think about this, right, the two du's cancel out. Differentials in a fractions work the same way. So then we have dy over dx. So this should be a pretty intuitive result, right? So let's put this to practice. So let's do practice problem number 16 for today, right? Practice problem number 16, right? So let's say that we have let's say that y equals to the, or why did I write this in? Right. Y is equal to 3x plus 1 to the 7th, right? Something like so. Normally, with what we know now, in order to take the derivative, we have to expand this whole thing, right? And this is going to be such a tedious process, right? To expand this whole thing and then go and try to take the derivative of every single term. There's going to be 8 terms we have to take the derivative of. It's going to be so complicated, right? But if you think about it, what we can do here is we can do the u sub that I was mentioning earlier and then take the derivative with respect to u, right? So yeah, so y prime, right? So y prime equals to what? So we know that y prime, we can also write this as dy of dx equals to dy of du times du of some dx, right? So essentially, the derivative of this function is going to be the derivative of y with respect to some u, and then we multiply it by the derivative of u with respect to x. So essentially how we are going to do this, right, is let's define u as being equal to 3x plus 1, right? So in this case, right, in this case, y is going to just be equal to u to the 7, right? So if we want to get this first part of the product out of the way, right? Right? If we wanted to get this first, take the derivative of y with respect to u, right? The derivative of y equals to u to the 7. We just bring the 7 out in front, and then it becomes u to the 6. So this is just 7 times u to the 6, right? And then we have to multiply the derivative of u with respect to x. So if u equals to 3x plus 1, u prime is just going to be equal to 3. And if you look at that, right, u to the 6, we want our final answer in terms of x, right? So at this point, all we have to do is plug in for u. So 3x plus 1 to the 6. And would you look at that? Look what we just did. We solved this derivative. And the trick here is that we substituted some u in for this function in order to be able to easily evaluate this power using power rule, something like so. And essentially what this is going to mean, right, we can actually extend chain rule to instead of doing something like this, right, this should be pretty intuitive as to why this works. But essentially what this means is that if h of x equals to g of h of x, right, something like this, where the two functions are enclosed, right, then f prime of x equals to g prime of h of x multiplied by h prime of x. So in this case, right, we're going to get quicker at solving this, right? But in this case, we don't have to use some, right? We just say that g of x is just going to be equal to x to the 7th, right? And then h of x is just going to be equal to 3x plus 1. So the derivative of x to the 7th is just 7x to the 6th. Plug in 3x plus 1 there, and then multiply for the derivative of h of x, which is just 3, right? So let's try a practice problem on this. This is going to be practice problem number 17 of the day, right? And chain rule is by far the derivative rule that will need the most practice. So we are only going to do we're probably only going to do 3 total problems of practice with chain rule, but believe me, you are going to need a lot of practice with chain rule, and then it's going to help you a lot. Because by the time you get to the AP test, it should be that you're able to look at that derivative and then with the chain rule, and you are able to solve that in your head. You should be able to solve it in your head. So we'll start by doing a more regular application of chain rule, and then I'll show you some way that we can actually extend our application of chain rule, right? So problem number 17, let's say that y equals to, let's do something similar actually. Let's do x squared plus 8 to the power of 10. Let's just make it, yeah. So what would y prime be? So in this case, right, we will break it up into two functions, right? So we can think about this as g of x, right, equals to x to the 10th, right? So this is the outer function, right? So remember, we're encapsulating this x squared plus 8. So we'll think x to the 10th. That's our g is our outer function. H will be our inner function, right? So h will be equal to x squared plus 8 because it's again encapsulated within the g, right? So then we know that y prime is going to be equal, by chain rule, right? By chain rule, y prime is going to be equal to g prime of h of x multiplied by h prime of x, right? And then solving this, right? What is g prime of x, right? If you solve these function out, g prime of x is equal to 10x to the 9th. And of course, like, if you want to start off with practicing like a u sub or something like this, right? That's fine. But I'd say if your practice is good once you are able to solve chain rule problems without like needing to do all of this mental. You just like say, oh, this is the inner function, take that out, take the derivative, right? You should get to a point where it's just that simple, right? So h prime of x, if we draw out an h prime of x, right, this is going to be equal to 2x. So all we have to do now is g prime of h of x, right? So g prime equals to 10 times x to the 9th, right? So if we plug in h of x, which is x squared plus 8, this is going to, So this is going to be equal, so y prime is going to be equal to 10. We plug in h of x, which is x squared plus 8 to the 9th, multiplied by h prime of x, which is 2x. So we can actually simplify this to 50x times x squared plus 8 to the 9th. So something like so, right? Now let's do another problem, but in this case, I'll show you a cool application using trigonometric functions, right? And this can help us avoid things such as power rule, or this can help avoid things, not power. Power rule is great, but this can help us avoid things like product rule and quotient rule, which are probably like our messy derivative rules that like we want to like try and avoid, right? And chain rule is so much better. So if you have the opportunity to choose between product rule and quotient rule and chain rule, always choose chain rule, right? You want to minimize the amount of quotient rule you're doing. Like ideally, you shouldn't be doing any quotient rule. It can lead to so many silly mistakes, right? But actually, chain rule will give you a way to check your work. So one strategy to do on the AP test is you can solve the problem using chain rule and then solve the problem using quotient rule, see if your answers line up. If they do, then you probably have the right answer. So something like that, right? So remember that for the AP test. But essentially, let's say that y is equal to sine of x multiplied by cosine of x. Is multiplied to sine of x multiplied by cosine of x. What is y prime? So normally what we would have to do in here is we would have to use quotient rule. No, we would have to use product rule in order to solve this. But from pre-calc, we know the identity that 2 sine x times cosine of x equals to sine of 2x, right? So we can actually simplify this, right? We can say y is equal to 1/2 sine of 2x, right? And then now if we're solving this using chain rule, remember this 2x is the inner function, so we take the derivative of this, right, which is 2, so it'll cancel out with the 1/2 in front. The derivative of sine is cosine, so this is going to be equal to cosine of 2x, right? So as you can see, right, this is so simple. This is such a simple way to solve this problem, right? And you can see how problems can be heavily simplified using chain rule, right? So yeah, chain rule is going to be our 9th rule, and in my opinion, chain rule is the most important derivative rule. Rule number 9, chain rule. Most important rule, right? So that's essentially what we are going to be. So that's essentially what we're going to be doing today, right? So now let's Yeah. So now if we for trigonometric functions and chain rule, right? Like I mentioned here with this 18th problem, right? Sorry. So 18th problem, right? If we have sine of something, right? Sine of something, essentially we can think of sine as our outer function. So if we're actually breaking this down, we can think of sine as the outer function. So g of x, we can think of g of x as our outer function, which will be sine of x. Well, actually, it's probably not visible. And then h of x will be equal to 2 of x, right? So remember, this h of x is encapsulated inside of this g of x. So that's essentially how we would apply it if we were using chain rule. So that actually works for all trigonometric functions, right? And that is going to be how we work to apply chain rule. Yeah. So that's actually, yeah, that's it for chain rule, right? So chain rule is this ninth rule, looks something like this, and is helpful to solve a variety of problems, right? So now let's go on to this thing called implicit differentiation, right? So up to this point, right, we've expressed most functions in explicit form. So for example, y equals to 3x squared minus 5, right? The variable y is explicitly written as a function of x. So, but however, we haven't actually... So essentially with implicit differentiation, right, we haven't actually looked at a problem that looks like so, right? So we haven't looked at something like if like we haven't looked into how we take the derivative of this thing, of this equation, right? So right now the y isn't isolated. So I mean, it should be obvious we move x to the other side, but essentially what we are going to do is we are going to use implicit differentiation, right? So how this works, right, is that we are essentially going to use chain rule in order to solve this, right? So chain rule can be extended to implicit differentiation, and in fact, this is just a form of chain rule. But essentially what we are going to say, right, is if we find dy over dx of xy equals to dy over dx times 1, right? So this doesn't even matter, right? So in this case, right, dy dx of 1, right? So in this case, right, what we're going to have to do is we're going to have to split this up using power rule, right? So we're going to take the dy of dx of... So in order to take the dy over dx, right? So in this case, right, we have an x multiplied by a y. But if we wanted to take the derivative of y, right, we know that the derivative of, like, y is actually an encapsulated function. So if we think about, like, so if we think about trying to find the derivative of, something like so, right, y to the 3 and trying to find the derivative, y is actually, we're going to have to use chain rule to solve this, because y is an encapsulated function, right? So if you think about this, if we break this up into two functions, right, g of x being the outer function, g of x equals to x to the 3, right, and h of x is equal to y. So y is actually some function of x, right? Meaning that we can't just say that, we can just take the derivative of x is just like, we don't have to worry about it, right? But if you think about it, this y is an encapsulated function. So we have to use chain rule in order to find, like, y prime. Actually, let's ignore that other problem this will be our problem number 19. Trying to find the derivative of this, right? So ignore that. Ignore this upper, sorry. Yeah, ignore the upper problem. Let's say we're trying to find the derivative of something like this, right? If we want to use chain rule, right, the derivative of this is going to be equal to g prime of x, right? So g prime of x is just equal to 3x squared. And then h prime of x, right, you can simply write this out at y prime or dy over dx, right? But h prime of x is simply just y prime, right? So if we want to do this, we have to use chain rule. So we take, g prime of h, right? Because g prime is equal to 3x squared, and we plug in h, which is y, we get 3y squared, right? But then we have to multiply by h prime of x, right? So that is going to be y prime. So you can see how we have to use chain rule in order to do implicit differentiation like so. So if we're doing if we're doing a problem like so, let's say problem number 20. Let's say that, let's actually go to that same problem. X times y equals to 1. Actually, it's not right. X times y equals to 1, right? So for this, right, we can use product rule, right? So this is going to be equal to x prime of y plus y prime of x equals to 0. Remember, the derivative of 1 is 0. This is also a common mistake we see amongst calculus students. They will often do this, right? And let's say based off of this, let's use implicit differentiation to solve for y prime, right? So implicit differentiation is essentially when you are taking the derivative of y, right? When you're taking the derivative of another variable, that is like implicit differentiation. So x prime, like the derivative of x is just 1. So it's just going to be y, right? And y. And then this is going to be plus y prime of x, right, equals to 0, right? So essentially here, right, y prime will be equal to, if we move negative y and then take it over x, it's going to be something like so, right? This is what y prime is going to be equal to. And then if we solve, what we'll have to do at this point, we just have to solve for y up here. So y is going to be equal to 1 over x, right? So if we plugged it in for here, we would see that y prime equals to negative 1 over x squared. And this actually gives us the same solution as if we were to just differentiate this top function. But essentially how implicit differentiation works is we are taking the derivative of y. This is also going to require like some practice, right? But essentially what you're going to do for implicit differentiation, you're going to be given an equation, and you're going to have to take the derivative with respect to x of y of both sides of the equation, and then you are going to have to solve it, right? So something like so, right? So before we end off today, so we've already seen how chain rule can be used to find dy over dx implicitly, but another important use of chain rule is to find the rates of change of two or more related variables that are changing with respect to time. So essentially what this means, right, is that let's say that let's actually, okay, you know what, the best way to do rates of change is to just do a practice problem. In fact, this will be the last one we do today, because this will be simply we're going to cover like implicit differentiation related rates in unit 3 as well. We're going to do applications of differentiation. So these are mostly, we're going to be introducing these topics essentially. So the last one of today, do problem 21. Problem 21. This will be the last one we do today. So once we solve this, right, we, like, you can see how this can be, like, sort of an application of derivatives, right? But this will be the last thing we do today. We're going to try to do a related rates problem, right? So let's say that we have, like, a conical thing filled, right? So with the radius of, let's say, 3, right? The radius is 3. The radius is 3, and let's say the height is 6, right? The height is 6. And then now we have water in this tank, right? So there's going to be, like, we're going to have, like water. There's going to be water in this tank. That is draining through the bottom, through this infinitesimally small hole, right? And let's say the water, right, because of this, right, the height of the water is changing at a rate of -2, right? So we're going to say, like, the height of this water is lowering by 2 inches every second. So it's going to be minus... Actually, just to make this more convenient, let's say it's -2 meters per second is the height of this. So what is the rate that the actual volume is decreasing? So what is the rate that the volume is actually decreasing at, right? So in order to do this, right, what we are going to do is we're going to say volume equals to, remember, for a cone, volume equals to pi over 3 multiplied by r squared times height. So now if we take the derivative of this, right, using implicit differentiation, we get that v prime, and the v prime is already isolated on one side, so that's good, right? Or actually, what is v prime at the time where radius is equal to 2, right? Where the radius is 2, right? So for this, if we take the derivative, right, it's going to pi over 3, right? And yeah, so then if we take the derivative of that, it's going to be r squared multiplied by h prime, right, plus 2h, times a, which is going to be, h multiplied by 2r multiplied by r prime, because we're using implicit differentiation, so like so, right? So what we are going to have to do in order to solve for this is we are going to have to make an equation that relates rate and height together, because we only know that the height is decreasing at a rate of -2 meters per second, so we have to relate height and rate somehow together. Height and radius. I keep saying height and rate. I don't know, what does it even mean? Height and radius. So because the height, if we take a cross section of this cone, right, you know that the max radius is 3 and the max height is 6. So because the cross section is a triangle, we know that the height is always equal to 2 times the radius, right? So, and if we are essentially trying to eliminate radius, right? So radius is always equal to height divided by 2, right? So if we plug that in, right? If we plug in radius is height divided by 2, and so so what we're going to do here, v prime equals to pi over 3, and then the r squared is going to be, this is going to be h squared divided by 4, and then we know that the rate at that height is decreasing is going to be -2, right? So something like so, plus height multiplied by 2 times radius, right? 2 times radius is just going to be another height, right? Times the rate that the radius is changing, because the radius is half of the height. We can is just going to be negative 1, right? So, and when the radius is 2, because the radius is half the height, the height is going to be equal to 4, right? So when the radius is 2, the height is 4. So if we plug in for this is going to be negative 8 plus, so height is 4. So this is gonna be minus 16 actually. Minus 16, right? So the volume of the tank is actually going to be changing at a rate of 12 pi meters cubed per second, right? So this is an example of a related rates problem where we're, for example, taking like a cone or a cylinder, and then like there's going to be water, for example, and flowing, and we use implicit differentiation, and we do something like this. Like this is going to be like a problem called like related rates, where two rates are going to be related to each other in some way, right? So essentially, yeah. So we'll leave off on that, right? But today we covered pretty much everything having to do with derivatives, and next time for Unit 3, we are going to be covering like some application of derivatives. So for example, if you think of a graph, finding minimum, maximum, extremum, points where it hits 0, things like that. And then also doing more of problems like these, where we are finding like, for example, if a ladder is falling, in terms of if a triangle is like changing, things like that. There's going to be a lot to cover next time, but hopefully today's lesson was fun. We learned a lot of new rules about derivatives, and yeah, so we'll see you in the next one then.